So this last chapter is on groups, or group theory. And a group is just another kind of algebraic structure. You know, we looked at, I'd say if there's one thing I could compare it to that we've seen already, it'd be kind of like the Boolean algebra, where we defined a set and we had some axioms that defined what made something a Boolean algebra. I think groups are objectively more interesting than Boolean algebras. So we define it similarly. So if we first take a set, and with a group you have just one operation. You have a set under one operation. In this definition, I'm just denoting it with a star because I'm trying to be really abstract about it. But in particular groups, maybe that operation would be multiplication, or maybe it would be addition, or maybe, you know, whatever we might choose to define it. So we have a set of objects, a set of elements. We have a single operation, and what makes something a group is these axioms. First of all, it has to be closed, which means that if we take two elements of the set, then A star B is going to be in the set, right? Smashing two elements together doesn't send us out of the set. That operation is associative, which means that the grouping doesn't matter. It means that if I have three elements, then A star B star C is the same as A star B star C. We saw that actually we saw that Boolean algebras, although this wasn't one of the axioms, Boolean algebras were associative, and we wrote that out and saw it in action a couple of times. A group will have an identity element. Here I'm just denoting it with an E, but it's the identity, which means that if I take any element and combine it with the identity, it doesn't change the outcome. So if you think about multiplication, our identity element is 1, because if you multiply anything by 1, you just get the same thing back. And every element has an inverse, and an inverse is something where if you smash an element together with its inverse, you get the identity. The operation need not be commutative, and that's really important. There are some cases where the operation in a group is commutative, and we call those abelian groups. But as an abstract, just in general, there are groups where the operation is not commutative, and we will in this chapter see an example of one or two of those. So, you know, I introduced this definition using really abstract notation like E for the identity and star for the operation. It's sort of easier to think of things like in the abstract. I'm just going to mostly adhere to using the multiplication notation. So I'll use like the dot and the 1 for the identity. But we should keep in mind that the results that we're going to show are true for any group. So we'll begin with just an example. We're going to show that the set of even integers under addition form a group. And the set of even integers we can denote with a 2z, right? So if I take that z that stands for the integers, put a 2 in front, that's the even integers, all multiples of 2. And so the set of even integers under addition, we would usually denote this as 2z comma plus in a set of parentheses. When we write about a group, it's important that we say not just what the set is, but also what the operation is. So to verify this is a group, we're just going to check those axioms that in the definition. Is it closed? Well, if I take an even integer plus an even integer, what do we get?
Even.
Yeah, an even plus an even is another even. If I wanted to write this out a little bit more rigorously, I would probably write it as, if I have like 2m plus 2n, well this is 2 times m plus n, right, just using algebra to rewrite this. And this is, of course, in the set of even integers. So if I take two evens, I get another even, and that means that the group is closed. The next bit that we want to check is, does it have an identity element? So think about what that identity element might be. Our operation is addition.
for addition would be 0?
Yeah. Yep, so the identity element is 0, and we want to make sure not only do we identify what that should be, but also just observe this is also in the set. We need to make sure that the identity element exists in the set that we're looking at. So it has an identity, because 0 is, of course, a multiple of 2. So we can check that off. The other one, or actually there's 2 left, one is associativity. And this, I'm just going to go ahead and say, you know, a lot of the time, depending on the examples that we're looking at, sometimes there's things that we really need to check. But on this one, associativity is really just inherited. We know that addition is associative in the integers overall, so it's definitely still going to be associative when we restrict it to the even integers. So I'll just write that this is inherited from the set of integers. And then the last thing was that we need to show that it has inverses. So if we're checking for inverses, what we need to do is say, let's grab an arbitrary element. So let's say we have, let's see, we're working with even integers, so let's grab 2m. So this is an element of 2z. What should its inverse be? Again, I'm looking for an element that I combine with this one under our operation of addition to get our inverse element, our identity element. So what should the inverse of 2m be? So we're taking our element 2m. What do I combine with it under our operation? What do I add to it to get our identity element, which is 0? Not a trick question.
Negative 2m.
Yes, thank you. So negative 2m, this is clearly true, and we would say, make the observation that negative 2m is also in the set 2z. It's also an even integer. So this means, these two things together means that inverses exist. So having checked all 4 of these, we know that the set of even integers under addition is a group. Even if other operations might exist in a set, you know, for example, it is possible to multiply 2 even integers for sure, but with a group, we just restrict it to, here's a set, here's the one operation we're looking at, and then we see if it's a group under that operation. And a quick typo here, or an omission. If G is a group with n, comma, this should read with n elements. So like G is a group, which means it's a set that's, you know, satisfies those axioms in the definition. If there's n elements, then we say n is the order of the group, and we indicate it notation-wise by using like the little absolute value signs. The same way that we'd indicate the size of a set anyway, like any set. But we use the term order of the group instead of just size. So here's another set that is a group under multiplication. If I is the square root of -1, then you take I, negative I, 1, and -1. As it turns out, that's a group of order 4. Because certainly the size of S is equal to 4. You can, this is really just an observe, and we'll work more with this a little bit later. We could even, you know, verify that this is a group. Certainly, if I take any two, actually I think the easiest way to do this is just to make a little grid. Oops. we can check closure just by filling in this table, right? So I times I is -1, that's in the group. I times -I is +1, and that's in the group. I times -1 is -I, and that's in the group. And for some reason, I skipped I times 1, and of course that's +I. You'll get the same. You'll get the same 4 elements that repeat themselves sort of in different orders in this table. I times -I, we've already found that is 1, and so on, right? You could fill in the whole table, and this would demonstrate closure. -I times a -I is -1, and -I times 1 is -I, and -I times -1 is a +I, and so on. You could sort of fill in the rest of this if you feel like. But it's a group of order 4 simply because there are 4 elements. What's the identity of this group? Keep in mind that it's really important that we know we're talking about multiplication. That's our operation.
Since it's multiplication, it would just be 1.
Mm-hmm. Yeah. Right, so I is the square root of -1. So we have these 2 complex elements, but then 1 and -1 are like the regular real numbers. So the identity element is 1. And in fact, actually, if we go through and just sort of fill out this table real quick, we could even verify inverses and stuff. So like the one row is really easy to fill out, right, because this just repeats everything. And then the bottom one would be -I, +I, -1, 1. So if I were looking for inverses, like let's say I wanted the inverse element of I, which we'll denote as like I to the -1. I'm looking for, what do I multiply by I to get 1, and how is that really easy to determine from the table we filled out?
Because you can just kind of like find the location of the I and where you multiply it by -1.
Well, not where we multiply it by -1. Like, if I'm looking for the inverse of I want to figure out what do I multiply by I to get +1, to get the identity.
So in the row I,
Yep.
you just go down to where you multiply it by -1, since we know -1 is the inverse.
-1 is not going to be the inverse. We're looking for the inverse of I.
Wouldn't that be -I?
If our identity were 0 and our operation were addition, but you already identified the identity as 1 because our operation is multiplication. Like, what I want to know is, what do I do? I times what gives me 1?
Oh. It would be -I.
Yeah. By doing the same kind of process you were just describing, right? We could say, all right, here's my I row, and I'll go through and I'll say, oh, look, here's where the 1 appears, and that happens when I multiply it by -I.
Yeah, I was looking at it below.
Yeah. It takes a little practice, right? Because like when you're working with groups, you kind of get, you definitely get some practice right off with being like, oh, whoops, what's my operation again? Like just having to go back and remind yourself. Because depending on what your operation is, changes what the identity is. So the order of this is, this is basically just an observation that this is a finite group of order 4. But what if we went back to that group that we were working with up here, the set of, this was the group of even integers. How big is this group? How many elements? How many even integers are there?
Infinite.
Yeah. So a group could be finite or infinite, right? So in example 6.2, this one we were working with up here with the I and the -I. This was a finite group of order 4. And example 6.3, which was actually the same one as the previous example, that's an infinite group. Are we having fun yet? All right, so now we're going to prove some results. the first biggie is that the identity of a group is unique. There is only one element that satisfies that definition of an identity that was part of the first page of this chapter, right? Where that's the one where we define what a group is, right? It's going to be closed, it's associative, it has an identity. As it turns out, it's only going to have one identity. There can only be one element that satisfies that. So in this proof, what we'll do is, let's suppose we have two identities. Let's suppose that 1 and E are both identities, are both identity elements of G. And what we're going to do is just show that 1 and E are the same element. Like if we start out supposing we have 2, as it turns out, oh look, so we actually just grabbed the same one twice. So let's work with 1. 1 is certainly equal to 1 times E, right? Like if E is an identity element, then I could do 1 times E, and that's the same as 1, right? That's what defines it as an identity element. But look at this product another way. I've taken E and I multiply it by 1, which is an identity element, so what does that give me?
E.
Yeah. Right, thinking of E as the identity tells me 1 is 1 times E. Thinking of 1 as the identity element tells me 1 times E is equal to E. So as it turns out, 1 is equal to E. And there is, let's see, how do I want to write this? So I'll just say, so the identity is unique. There is only one identity element. So far, so good? So we know that a group has to have an identity, and we showed that there's only one. Now we're going to work with another one of those axioms that said that every element has an inverse, and as it turns out, each inverse has but one. Each element has but one inverse, right? The inverse of each element in a group is unique. And we're going to do it, we're going to approach it kind of the same way. So let's let A be an element of G. And let's suppose A has two inverses. We'll show that they're the same element. So let's suppose B and C are both inverses for A. Then, let's take our element B. B is certainly equal to B times 1, right? Because there's every group, we know the identity element exists, so I can always write B as B times 1. At the same time, 1 is always going to be the same thing as an element times its inverse. So I could rewrite 1 as A times C, and I can do this because C is an inverse of A. If C is an inverse of A, that means if I multiply A by its inverse, I get 1. So I can replace 1 with the product A times C. At this point, though, now we can use the fact that a group is associative. The operation is associative. So we can write this as B times A times C. So it doesn't matter how we group the operation. So now look at what we have here, B times A times C. But let's focus on the part in the parentheses. What should B times A be equal to?
B is also an inverse of A, it should be equal to 1.
Yes, yep. And what is 1 times C? Not a trick question.
It'll be C.
Yeah. So now, look, here's what we have, this nice big long equals, right, string of equations. B is equal to C. And that means that the inverse of A is unique. Questions on that result? Okay. All right, so our next result says that if for any element in G, the inverse of A inverse will just be A. This one's actually super easy to prove. All we're going to do is show that A inverse times A. What do we get when we take A inverse multiplied by A? 1, yep. And this would be the same as A times A inverse, right? I mean, again, if I ask what is A times A inverse, I think everybody would just say, oh, it's got to be 1 because I'm multiplying an element by its inverse. And this is really all the proof that we need. The only thing we're going to do is observe that this satisfies the definition for an inverse. I mean, we're saying A is the element that I have to multiply by A inverse to get 1. That's exactly what it means to be an inverse. So A satisfies the definition of inverse for A inverse. Okay, so now we know that not only is an inverse element unique, but the inverse relationship is sort of reciprocal, right? If I find the inverse of A, then that means I've also found the inverse of A inverse. Another result. The inverse element of AB is B inverse A inverse. Note in particular how we've changed the order. It's not A inverse B inverse, it's B inverse A inverse, and that's actually super important. So we're going to show this simply by checking, right? We can just do the computation. If the inverse of this is equal to this, then when I multiply them together, we should get 1. So that's all we're gonna do here. So let's check. If we take AB times B inverse A inverse. This is what should give us 1. So we're just going to apply the axioms, part of the definition of what makes a group a group. I think I'll start with using the associative property and say I can kind of group these in any old way I want. So I'm going to look at this as A times B inverse times A. What's important to note here is I'm not actually changing the order. A, B, B inverse, A inverse. That order is maintained here.
Shouldn't that last A be A inverse?
Yes, thank you. Good catch. And I'll use the associative property again, which says it doesn't matter which way I group this. And we'll say that this is A times B, B inverse. I want to focus on doing that part first. And what's the advantage to that? What do we get with B times B inverse?
Well, now we can just change
Yep, so we get A times 1 times A inverse. And of course, A times 1 is just A. And then we have A times A inverse, and that gives us 1. And that's enough for us to show that the inverse of AB is B inverse A inverse. It just satisfies the definition. We've done this really, we did this proof probably more rigorously. Like, we really just sort of using the definition in a very rigorous way, like making sure we were saying, okay, we're going to group it in this way, and now we're going to group it in this way. The really kind of quick and dirty version of this would look like AB times B inverse A inverse, and just say, look, first, these two inner terms, they kind of cancel each other out, they collapse, and then we get, A inverse, and now these guys sort of collapse to 1. That's essentially what we did. We just sort of were a little bit more careful about crossing the T's and dotting the I's. Okay, so our next theorem we're not going to prove, actually some of these might be part of the exercises. So if a lot of these properties will seem like they should be true because they look just like regular algebra properties. But we have to be careful about knowing what kind of regular algebra properties that we know and love extend to working with groups. So first of all, we're just denoting if I take the inverse of A and raise it to the k, we're just going to denote that as A to the negative k. And A to the 0 will denote the identity 1. The first and the last properties, these are basically the same property. Both of these properties say that the inverse of A to the n is A to the negative n. Here it says it just by saying that it satisfies the definition, right? Because if I multiply them together, I get the identity. Here it says it by notationally, right? The inverse of A to the negative n is A to the n. So those are really the same. And if I were going to show, if I were going to demonstrate that D is true, I would just simply rely on A, like they're equivalent statements. And these properties, again, I'm not going to sort of belabor the explanation. Again, it seems like they ought to be true because they're properties we know from like regular algebra. And they're basically a result of us adopting the multiplication notation. We could rewrite these in using like an addition notation if we wanted to. One thing that I really want to point out here is that not all of the like exponent properties from regular algebra follow us. For example, in regular algebra, we're used to being able to say that AB to the n is A to the n, B to the n, but this is absolutely not true for groups. It's only true if your operation is commutative for groups, and that's not always the case. A group is not a Boolean algebra. Remember, one of the big results in a Boolean algebra was the idempotent property that said A times A is equal to A, and it was also true for plus. With the Boolean algebra, we always had two operations. A group is not a Boolean algebra. If there is an element where A times A is equal to A, then that element is the identity. There's only one element that satisfies that. So a group is not a Boolean algebra. So here's an interesting result. If we have a finite group and A is an element of G, then there's some power of A is equal to 1. Like, so I just think about A times A times A times A. If I just think about the elements I might generate by doing that over and over again, this says eventually we'll get to 1 for some positive integer, S. So let's prove this. And we're first going to just appeal to the fact that G is a finite group. There's only finitely many elements in G. And now think about generating elements. Taking A, just the single element A that's in the group, and then just multiplying it by itself. Just find A times A, A squared, A cubed, A to the 4th, A to the 5th. And we're just going to keep doing that forever, right? I could generate as many elements as I want. But if G is a finite group, what that means is eventually I'll replicate some. So let's sort of write that out. How do we want to say that? Since G is finite, then we could say a to the j is equal to a to the k for some j not equal to k. Right, this is just saying eventually I will replicate results because it's a finite group. If it were an infinite group, I could probably just go forever and ever and keep getting different elements. And this is because G is finite, that means there are finitely many distinct powers of A. So let's suppose, without a loss of generality, if J is not equal to K, one of them has to be bigger than the other. So let's suppose that J is less than K. And let's find a product. Let's find A to the negative J times A to the K. And let's work with this. The first thing we're going to appeal to is the fact that when we said that as we were kind of generating, because this is a finite group, as we're generating powers of A, eventually I'll get to a pair of values that are the same, right? When we said A to the J is going to be equal to A to the K right here. So I'm just going to substitute that for A to the K. I'm going to substitute A to the J for A to the K. So we get A to the negative J times A to the J. And what do we get when we multiply A to the negative J times A to the J? 1, yeah. They are inverses of each other. That was one of the results that we reviewed quickly on the previous page. On the other hand, what is another way to write A to the negative J times A to the K? If we look back on the previous page here, just using this property here, but I guess in this direction, we have a product, so we can write it as a single power of A. So this is A to the K minus J is equal to 1. And now finally, let's let S equal K minus J. And now we assumed without a loss of generality before, we said suppose J is the smaller of the two, and if J is less than K, then K minus J must be greater than 0. So A to the S, which is A to the K minus J, is equal to 1. And that's the result we wanted to show. Okay. Questions on that result? All right, let's do one more. So let's let G be a group. We grab an element A and G where A to the S is equal to 1 for some S. If P is the least positive integer, such that A to the P is equal to 1, then we know P will divide S, and we say that P is the order of A. Like maybe there's lots of powers you could raise A to get 1, but one of them will be the smallest. And any other power of A that you could put, any other power you could raise A to get 1 will have to be a multiple of P. So So let's begin. Let's suppose that p is the least positive integer such that a to the p is equal to 1. If that's the least power such that a to the p is equal to 1, then again, think about that process where we take a and we just keep multiplying it by itself to generate different elements of g. If p is the first time that we get 1 by going through that process, then we know for sure we have generated at least some distinct elements in the group. So we'd have 1, a squared, all the way up to a to the p minus 1 are distinct. Those are distinct elements, and there are no repeats in this list. And remember, of course, that 1 is also the same as a to the 0. And we're not including a to the p on this list because, of course, as soon as I get to a to the p, I've repeated the 1 element. Now, let's say if n is greater than p, so if n is greater than p, right, I'm taking some element bigger than this smallest power that gets us to 1, then a to the n will be equal to some power of a that's already there. So I'll write that as it's going to be equal to a to the r for some r that's in this set from 0 up to p minus 1. All this says is that if I take some power of a that's bigger than a to the p, like if the exponent is bigger, because these are all the distinct ones, then I know that I'm going to have to repeat one of those values. And I know it'll be one of these values, and because n is greater than p, we can write n as p times q plus r, just using the division algorithm here. And this is for some integer q and r in this set. So this is just using the division algorithm. So now let's revisit the a to the n, right? We know it's going to be a to the r for one of these, but let's revisit that using this expression that we found. A to the n is a raised to the pq plus r, and now I'm just going to use our sort of exponential like multiplication notation to rewrite this expression. Those results that were a couple of pages ago, that sort of list of results. This is the same as a to the pq times a to the r. And again, a to the pq, I can use another property, and this is a to the p all to the q power. Now, by supposition, a to the p is equal to 1. So if a to the p is equal to 1, then this element is 1 raised to the q power, and that also has to be 1, which means this whole thing is just equal to a to the r. Now we're getting pretty close to our desired result. Here's what we're trying to show here. We want to show that if there is any integer, right, such that a to the integer s, such that a to the s is equal to 1, then p is going to divide that power. what we've done so far is said, well, let's suppose if I raise a to any power that's bigger than n, not only will I then repeat some of those powers, but we can see that which power we'll get, right, in the list, simply by using the division algorithm to rewrite that power and using these properties of the operation. So now, let's let S equal some P, Q plus R. And in particular, I'm switching to S now because I'm going to consider an integer where a to the S is equal to 1. So for some Q and Z and some R from 0 to P minus 1, now, if a to the s were equal to 1, the only way that could happen, right, if s is pq plus r, we know that a to the s will be the equivalent to a to the r. The only way then that this whole thing could be 1 is if r is equal to 0, right, because it would have to boil down to this element being a to the 0. Like, that's how we'd get 1. And if r is equal to 0, that means S is just equal to PQ. And of course, now at this point we can say P divides S. This now gives us sort of two notions of what we mean when we say the order of something. The order of an entire group is just how many elements it has. The order of an element, like a single element, though, is just the smallest power that I can raise it to get to the identity. And what we know is that there will be some smallest power I could raise an element to get to the identity. If there's any other power that I can raise it to get to the identity, it'll just be a multiple of that. So we get this sort of cyclical behavior if you just think about taking an element A and smashing it with itself over and over again to produce elements. You get this cyclical behavior for a finite group at least. If we get to 1, it'll just then start generating the same elements over and over and over again. Okay. We had been talking about we've been talking about a bunch of things, but one of these things, and it was the very last thing that we talked about, we knew that there would be some, in a finite group, there would be some power we could raise an element to, for any element, that there would be some power I could raise an element A to get the identity element. And in theorem 6.7, which was the last thing that we proved, we kind of expanded on that and we said, okay, if we have some power, right, a to the s equal to 1, if p is the least positive integer such that a to the p is equal to 1, then p must divide s. And this smallest power, this least positive integer, where that would happen, where I could raise a to that power and get the identity, we call that the order of a. So now we have these two concepts of the order in a group. The order of a group itself is just the number of elements, and the order of an element is the least power that I could raise it to get the identity element. So let's look at a specific example back to this group with 4 elements. It's a group under multiplication. I think we even filled out the sort of multiplication table for these elements. What is the order of I? And when we denote this, we use the absolute values. So when we want the order of I, I would sort of write it that way. And we're basically asking, I to what power is equal to 1? And we're looking for the smallest possible value that could go there. Remember, I is the square root of -1.
So we want, where Or is it about the, okay.
Oh,
Two,
yeah.
Sorry. Isn't it the second power?
It's not the second power, and in fact, I'm going to adjust what I've written here. I'm going to bring this down here, because this is related, right? But I to whatever power is equal to 1, that's the number that goes here. It's not 2 because I squared is equal to negative 1. And the identity element is 1.
Okay.
So what's I cubed?
The I cubed would be 1.
Nope.
No.
So I cubed is I squared times I, right? So, and I squared is negative 1, so I cubed is negative I. So there's I cubed. And what's I to the 4th?
I squared times I squared.
Uh-huh.
Would be negative 1 times negative 1. Would be 1.
Yeah. So that means that the order of I is 4. What's the order of negative 1?
Pretty sure we just.
Well, you might have it. I mean, negative 1, what power do we put on negative 1 to get
I
1?
was thinking that it's just the power of 2.
Yes, that's it. Right? Because negative 1 squared is 1. And there's no smaller power of negative 1 that will give us 1. 2 is the first time we get there. You know, if you're not sure what the order of an element is, you can, kind of like we did with I, just kind of go through it. I to the first is obviously I. And then we get I squared is negative 1. That's not the identity, so the order can't be 2. I cubed is negative I. That's not the identity, so the order can't be 3. The very first time we get to 1 is I to the 4th, so there's the power. In fact, note that... So I get we've answered the questions posed in this example, but as we were going through and finding these different powers of I when we were looking for the order, note that I to the first, which I kind of left out, but is I. I squared is negative 1. I cubed is negative I, and I to the 4th is 1. In fact, we got all of these elements. And we'll talk more about what that means as far as the structure of this group goes. But that's significant. And it doesn't always happen. Notice that doesn't happen with negative 1. With negative 1, I to the first is negative 1 to the first is negative 1, and negative 1 squared is 1. I'm not going to generate I or negative I just from working with negative 1. So next, we're going to look at subgroups. We'll define a subgroup, and it's basically what it sounds like. You take a group. If there's some subset of those elements that is also a group in and of itself, a group in its own right that satisfies those definition of a group, then that's a subgroup. A subgroup is just a group within a group. So, in order to check that a subset is a subgroup, we'll note that because it's contained, if G itself is a group, right, we wouldn't use the term subgroup if it wasn't contained in a larger set that is a group in and of itself. So the associative property would be inherited from the larger group, so there's no need to check that. But what we would need to check is that it's closed. We know G is closed, but we want to make sure that H is closed. That if I take two elements in the smaller subset and I smash them together, it doesn't send me outside somewhere else in the group. And we want to make sure that it has inverses. So those are the basic things that we need to check. Obviously, yes, it does need to have the identity as well, because a group needs to have an identity element. So as a quick example, just to kind of get our sea legs with this, the integers are a group under addition. And, the 0, the identity element is 0. And the inverse elements would just be the negative. So if A is an integer, its inverse is negative A. So we're going to show that the subset MZ is a subgroup for any positive integer. So by which we just mean the multiples of M in the integers. So first, does it have the identity? Is 0 in MZ? Is 0 a multiple of M? And we've actually already answered this question in a different context. previously, like, I don't know, back in chapter 2 or 3, something like that, 2, I think. Maybe chapter 1. It was when we were looking at equivalence relations, I think. So we want to know if 0 is a multiple of m. Right? What that means is we want to know, is 0 equal to m times something? Can I find an integer that goes in here that makes this equation true?
If that's 0.
Yeah. Yep. So 0 is a multiple of anything, right? We looked at this when we were doing equivalence relations, and we were defining the relation where we said A and B are equivalent, are related if their A minus B is divisible by M, right? In fact, we even kind of went through when we were showing that it was reflexive and transitive and symmetric and all that. So yeah, this gets a yes. So we can check that off. Next, is it closed? So if we take two multiples of m, if I take m times a, for example, plus m times b, just using a little bit of, regular old algebra, we could factor out the m, and we get a plus b, and that's a multiple of m. So this itself is in the set mz. So this, we could check this off. And then the last thing we need to check is, does it have inverses? Well, to examine that, we have to just pick an element in mz, so like maybe m times a. What would its inverse be just in the larger set of integers? Keep in mind that our identity element is 0, on our operation is addition. So what do I add to MA to get 0? Not a trick question, by the way.
Negative MA?
Yeah, negative MA. So its inverse element would be negative MA, and which we know exists in the integers, right? Because Z, the integers, is a group itself. We just want to make sure that that exists in this subset. And of course, negative MA is still a multiple of M. So MZ does contain inverses. And the fact that addition is associative is inherited from the larger group, so we don't need to check that. We know it has the identity, it's closed, it has inverses, and that means that MZ is a subset of Z. And notationally, the way we write that for the subset symbol is just the less than or equal to symbol. So there's sort of a simple, example of a subgroup, right? So we have the larger group is the whole set of integers under addition. But if you look at the multiples of m, if you just pick any positive integers, like for example 3z, all the multiples of 3, that's a subgroup under addition. The multiples of 5, that's a group under addition, that's a subgroup of z. Another example that we won't do a whole lot of work with right now, but if we look at just the positive real numbers, so eliminating 0 and no negatives, just the positives, that's a group under multiplication. And you could do a quick check. This is, by the way, why we have to eliminate 0. Under multiplication, the identity element would be 1, and the inverse element for any real number would just be its reciprocal, right? So the inverse element of a half would be 2. The inverse element of pi would be 1 over pi. 0, of course, has no inverse because 1 over 0 is not defined. It's not a real number. So that's why we're restricting ourselves just to the positives. It's also closed, but if we look at this larger group of the real numbers under multiplication, if we restrict it to just the rationals, that's what the Q means. So these would be positive rational numbers. that's the fractions, then that's a group, that's a subgroup of the positive reals under multiplication. When we talk about having a, we said the positive reals is a group under multiplication, and then we say, oh, well, the positive rationals is a subgroup. We are talking about the same operation. When we use the term subgroup, we are retaining that same operation. All right, so let's look at these residues, mod 6. We looked at these, I think, in chapter 2. So we know that Z6 consists of 0, 1, 2, 3, 4, 5, right, where these are representatives of like the equivalence classes when we define that equivalence relation. So we're going to verify that this is a group under addition. So let's do that first, and then we'll look at that subgroup. So is Z6 a group? Well, so the first thing is it closed? And so right now I'm just going to kind of review a little bit of what we already did in chapter 2. If I take two elements in Z6, A bar plus B bar, we said this is the same as A plus B bar. I can just add the integers and then reduce mod 6 at the end. And that is in Z6. So it is closed. What about the identity? If this is a group under addition, what's our identity element?
There's addition.
Mm-hmm.
Isn't that 0?
Yes. Yep. So and so this is just us seeing the addition is 0, and look, 0 is in the set. So just checking that we have that identity element in Z6. So that's all set. Inverses. And I think this is something we already looked at before back in chapter 2, but the negative of, because our operation is addition, then our inverses are like the negative of this number. So the negative of A bar is just negative A bar. And if you take some number, that just means we could take whatever negative A is and then reduce that mod 6. And that will have a home here, right? We know this, by the way, we've already done the hard work in establishing this back when we showed that that was an equivalence relation. And we know that the equivalence classes partition the set, right? Like every integer will have a home in one of these, which means whatever integer negative A is, when I reduce it mod 6, it's going to be one of those 6 values. So this is in Z6. For example, negative 2 bar is 4 bar. And then the last thing that we need in order for something to be a group is the associative property. But this one, there's not a whole lot to show because this is inherited from the overall larger set of integers. So Z6 is a group. You could even show this. I guess I could say by brute force, like if you made an addition table for the elements of Z6, and then showed, then you could identify the inverse of each one. You could show that when you add 2, it will have a home. It'll be one of the 6 elements to begin with. But this is a nicer, I think of it as a nicer, more general proof because this would hold for any value. This same argument works for Z10 or Z13 or Z whatever, and I don't have to keep making, addition tables. So now what we're going to do is verify that this subset, which consists only of the element 0, 2, 4 out of Z6, that's in fact a subgroup. So so let's see, is it closed? Now, when we're looking at just these few, this would be fairly simple to just sort of work out kind of by brute force. For example, there's only 3 sums we can check, right, that we need to check. 0 plus 2, 0 plus 4, 2 plus 4. Oh, I guess there's a few more. Hold on. Let's do those 3 first. So 0 plus 2 is obviously 2. 0 plus 4 is obviously 4. 2 plus 4 is 6. What is that?
That'd be 2, right?
6 mod 6.
So 0.
Yeah, that one's 0. And then let's see. What else do we need? 2 plus 2. That's 4. 4 plus 4 is 8. And what is that? Mod 6.
2.
Yep, that's 2. And I guess we could check 0 plus 0. It's clearly going to be 0. Right, and so here's the point. Here's what we want to observe. We knew, by the way, from the work we already did, we knew that when we added, this would still leave us in Z6. What we're making sure to observe is that all of these things are, in fact, in S. Right? So when I just add things within the smaller S set, it doesn't send me outside. So I know S itself is closed under this operation. And inverses. Oh, actually, before we do that, one quick thing. It has the identity, and that's that needs no showing other than to say it because clearly it's in the set. But now that we've mentioned the identity, we can find inverses. So the identity is always its own inverse. So what's the inverse of 2? So our operation is addition, yep.
It'd be 4.
It'd be 4, yep. And of course now the inverse of 4 is 2. And again, we knew that these inverses existed in Z6. So the thing that we're actually checking is that both of these are in fact in S. They're both in that smaller group. So the smaller group itself is closed and it has all its own inverses that it needs. Okay. Are we ready for more?
Sure.
Okay. Now, when we have something that we know is a group and we're trying to see, oh, is this other thing a group, or, like a subgroup, you could go through and you can just sort of check off, does it have the identity? Is it closed? Does it contain inverses? But there's actually a sort of one-stop shopping test to see if something is a subgroup, and we're going to prove that result. It's a pretty useful result, so we're actually going to prove this. We call it the subgroup criterion. So it says, let's suppose we have a group, and I'm going to use the multiplication notation here. Let's say we have a group G, and H is some subset of G. Then that subset H will in fact be a subgroup of G if and only if for any 2 elements I might pick in H, so if X and Y are 2 elements, then the product X times Y inverse is in H. If that's true no matter what 2 elements I pick in H, then H is a subgroup, and vice versa. If H is a subgroup, then that will be the case. So we have 2 directions to prove. The first direction is fairly straightforward. So we're going to suppose that H is a subgroup of G. And we'll let X and Y be 2 elements of H. We want to show that XY inverse is in H. Well, what we have to go on is that H itself is a group. So because H is a group, then it has to contain inverses. So we could say for sure Y inverse is in H. And also, because G is a group, it has to be closed. Sorry, because H is a group. So now it's closed, and what I'm going to do is pick, so that means no matter what two elements I pick, when I smash them together, it's going to stay in H. So the two elements I'm going to pick here are the element X and the element Y inverse that we said we know has to be in there. And that's the end of that direction. Right? We're trying to show that if H is a subgroup of G, then for any two elements, X, Y, and H, this product will be in there, and we've established that. You get a lot from knowing that H is a group. So the other direction takes a little bit more work. So what we're going to do now is we're not going to suppose H is a subgroup anymore. We're just scaling it back to saying we know H is contained in G. It's a subset. And we're going to suppose that no matter what two elements I pick, if X and Y are any two elements in H, that X, Y inverse is in H. And this is what's going to be the important bit of our assumption here, is that for all elements I might pick, no matter what two I pick, that if I take X times the inverse of Y, then that will be in H. So first we're going to establish, right, we're going to show that H is a subgroup of G. We need to show that H is a group, basically. So we're going to establish that it has the identity. So if H is a subset, a non-empty subset, that means we have at least one element in there. So let's grab an element. Say if we have some element X in H, then again, this thing that we get for free is no matter what elements I pick for all X, Y, and H. We know this is in here. So I'm going to use this fact if my elements are X and X. If my elements are X and X, then X times X inverse is in H. And what is X times X inverse? Yeah, yep. That's what defines it as being the inverse, right? Is that if when I smash it together, I get the identity element, and we're using the multiplication notation, so that's 1, yeah. So X times X inverse is in H, which means that 1 is in H. So H has the identity. Now that we've established that it has the identity, let's look for inverses. So, well, let's see. Because 1 is in our subset, then for some element I might pick, let's say I call it y this time. Then for some element y in H, now I'm going to use that same product that I get. This is my assumption that no matter which two I pick, that product, x times y inverse, will be in H. I'm going to use that now for 1 and y. And of course, if I multiply anything by the identity, I just get itself right back. So this means that y inverse is in H. And so H has inverses. You know, once you get the identity element in there, then using that same product that we know will be in the group means that we'll have inverses. And now lastly, the last thing, does anybody know what the last thing to check is that we haven't done yet?
Isn't it this closed or not?
Yeah, if it's closed. And I'm approaching it in this particular order for a reason. So for closure, because we're going to use what we've already shown, we need the existence of y inverse to help us show closure. We needed the existence of the identity to help us show the existence of inverses, and we need to use the existence of inverses in order to show closure. So let's let x and y be elements of H. We already know that y inverse has to be in H because H contains inverses. So now I'm going to take that same product that is our assumption in this part of the proof, that if I take an element times the inverse of another, that product will always be there. But I'm going to use that product for the elements x and for y inverse. So x times the inverse of y inverse is in H. What is the inverse of y inverse?
Is it not 1?
It is y, yep. That was one of the things we showed last time. So we grabbed a couple elements, x, y, and h. We show that their product now, x times y, is in H. That means that H is closed. And it follows that H must be a subgroup of G, not just a subset. How's that? Questions on any part of that argument that we made?
Actually, yeah, it's probably more of a clarifying question. For the identity, we just did x times x inverse. Can you go over what x inverse would be and why we get 1?
Oh, okay, yeah. So first of all, in this proof, that's a good question. In this proof, we know that H is contained in G, right? So if we have an element of H, we know it has an inverse element somewhere in G at least, because G itself is a group. And we know the reason we get x times x inverse is we're using this fact, our assumption on this part of the proof is right here, is suppose that for all, no matter what elements we might pick for x and y, that the product xy inverse is in there. So that holds even if we pick x and x. So we're saying for x and x in H, then x times x inverse must be in there. We're letting x play the role of both x and y in this assumption. And that's a bit, it's the for all part. That's the big part of this supposition. So we know that x inverse is somewhere in G, it has to be because G contains inverses.
Mm.
By definition, then, if I multiply an element by its inverse, that has to give me 1
Oh, right, so that's just a definition of,
of an inverse. Yeah.
okay.
Maybe that was a longer, maybe that's exactly what your question
That-
was,
that
and
was my
okay,
question.
all right.
That's fine.
Other questions? Okay. All right. Last time when we were talking about the order of an element and how, you know, if not just the order of an element, but also, I think it was when we were proving, oh yeah, this one, and we said, suppose we have some least positive integer, and we could just keep smashing A together with itself and kind of generating these. And I don't remember if it was Hunter or Riker, but you made some sort of comment about, oh, so it's all sort of cyclic behavior. And you will get that behavior with a particular element, like if you just keep doing that. It does not necessarily mean that the group itself has to be cyclic, although those do exist. But you will get some cyclic behavior if you take an element and just sort of keep smashing it together with itself. So that's what we're going to define here. If you do that, so we're not assuming anything about G right now. We're not even assuming that the operation's commutative. But we know if there's some least positive integer, P, such that G to the P is equal to 1, right? So I eventually get to the identity element. Then we look at all those different distinct values that we get from distinct powers of P. So notice here, G to the P, that's our 1 element. This is guaranteed to be a subgroup. That's basically what this theorem says. We're not going to prove it, but I think it pretty quickly passes the I believe it test, because if you smash together 2 powers of G, you're going to get another power of G, right? It's not going to send you outside powers of G. It does have the identity element, because G to the P is equal to 1. And it wouldn't be too hard to show that it contains inverses. Take some power of G, and you could find some other power of G that will get you to the identity element. I mean, it takes probably a little bit of work, but I think it gets, you know, we could get to the point where we're kind of believe that seems totally plausible. This group, this subgroup that we get, we call it a group generated by the element G. And we use the little angle brackets here to denote that. So when you see the angle brackets around an element, we're talking about just taking an element G and kind of smashing it together with itself over and over again and just seeing the distinct values that we get. And as we kind of observed a little bit last class, this is cyclic in nature. Let's return to that group we were looking at before that has, you know, it was I, negative I, 1, and negative 1. We know it has the identity element. I think we've examined why it's a group before. It's a group under multiplication. We even found inverses once. This group is cyclic, and in order to show that a group is cyclic, you need only find the generator. You need only be able to say this group is generated by this one element. What element generates this group?
Is it I?
Yeah. Yep. So this group S is generated by the element I, and that's because, I'm just going to kind of rewrite what we've noticed on the previous page. I to the first is 1, I squared is negative 1, I cubed is negative I, and I to the fourth is 1. So this one element generates all elements of the group. We can extend this idea of generating a group with an element by saying, what if we maybe take a look, maybe if we grab another element, right? So let's say we have a group, G, and I take some subset. It doesn't have to be a subgroup, just some collection of elements. I don't even care if the identity is in it. Like, I'm not at all concerned with whether or not A is a subgroup. And I just say, okay, I'm going to take elements of A and just start smashing those guys together and seeing what elements I can produce. Just like we would if we were restricting ourselves to a single element and just looking at the powers of G that we got. But I'll just put some more elements in there and just see what we can generate. Then we will generate a group that is a subgroup of G. You will generate a group of some kind. If A generates that subgroup or that group H, and no proper subset of A generates the same group, meaning all the elements of A were really required to get all of the elements of that group, then we say that A is a minimal generating set, and we use the angle brackets again to denote the group generated by those elements. If A consists only of a single element, then it's a cyclic group. So that's basically what it means to be cyclic, is that you can be generated by a single element. If we go up here, back to this group that we were looking at, I could consider the fact that I could generate these same elements if I take I and -1. I will generate all the same elements. So I could also say this, that S is generated by those two elements. But I don't need them both, right? I and -1 is not the minimal generating set. I get all the elements just by taking the element I, just by starting with that one. So we would say that these two are equal, that I -1 is not a minimal generating set. It will generate the same group, but describing this group as being generated by I and -1 wouldn't really be considered fully correct, because it doesn't really convey the fact that it's really, if you're trying to describe a group, you want to make sure that you can give a minimal generating set. And while these two are equal, we get more information by writing it this way. When I see that this group is in fact just generated by the single element I can tell right off that that's cyclic, whereas that is not apparent when I write it that way. We had left off, we defined what cyclic group is. We kind of talked about the notion of how you can kind of just generate subgroups by picking elements and kind of smashing them together, right? We call that a generating set. If we generate a group with a single element, then that's what a cyclic group is. So now a new definition is finding a coset of a subgroup. So if we have a subgroup of G, not just a subset, but in fact a subgroup, then what we can do is take a look at sets that we can produce by taking elements of the group and finding the product A times H. So this A times capital H, that defines an entire set. So the little element A here can range through all elements of the group G, right? And then we just keep finding all the products for a particular A. We smash it against all the elements of G and we see what set we get. And then we do that again for another element of G and another element of G. And so we can make a whole bunch of sets. We call them, they're left cosets. If the G element A there is on the left, and analogously we could define a right coset. We'll mostly be sticking with left cosets, but you can develop a lot of the same, all of the same results, in fact, if you work with right cosets. So just to see what we mean, let's say we're working with the group of the integers under addition, and H will be the group 5z, multiples of 5. And that is a subgroup. I think we even established that it's a subgroup, maybe in a previous, or something similar, right, in a previous exercise. We're going to find the cosets of H in Z. So let's begin. We start by taking an integer. Maybe we could start with 0. And this notation here in the general notation, I'm using like the multiplication notation, but obviously we're going to use the operation that is defined in our group. So the 0 coset will be 0 plus h, and this will be the set 0 plus little h for every element h in 5z. So I pick an element of G, and then I add it to every element of 5z. So if H is in the subgroup 5z, that means it's a multiple of 5. What do I get if I add 0 to a multiple of 5? Not a trick question.
It's still a multiple of 5.
Yeah, so as it turns out, this is going to be the same set. Minus 15, minus 10. So now I'll pick another integer, say 1. So now I'm going to take 1, and I'm going to find the sum 1 plus h for every element in 5z. So now what I'm doing is I'm taking the subgroup that consists of all the multiples of 5, and I'm adding 1. So I'm going to get a set that just consists of all the integers that are 1 more than a multiple of 5. Similarly, right, we'll keep going. We'll do the same with 2. So we get minus 13, minus 8, minus 3, 2, 7, 12, 17. And keep going. The coset 3 plus h, what we might call the 3 coset of h, is going to be, you know, any multiple of 5 plus 3. So this will look like minus 12, minus 7, minus 2, 3, 8, 13, 18. Find the 4 coset of h. So I'm going to take multiples of 5 and add 4. Minus 11, minus 6, minus 1, 4, 9, 12, gosh, what's wrong with me? 14, 19, and so on. What happens when I now find the 5 coset of h?
It's the same as the 0.
Yeah, it's the same as the 0 coset. Right, if I take a multiple of 5 and I add 5, I'm going to get another multiple of 5. And so these right here, these are all the cosets. There are 5 cosets of h. And one thing we might observe here, every integer is accounted for. You know, I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you know, and then you go backwards to find all the negatives. All the integers are accounted for. Notice none of them overlap. And so if I have a set of sets, right, and all my integers are accounted for and none of them overlap, that means that the cosets partition the integers. And that's always going to be true. If you have a subgroup, you have to make sure you're starting with a subgroup, and you find the cosets of a subgroup, then those cosets will always partition your group. In fact, that is our next result on the next page. Lemma 3 says that if we fix a subgroup, H of G, then the left cosets partition G. The same would be true for the right cosets. We're just sort of going to be establishing all of our results for left cosets. Not only that, but notice, and I guess this is kind of obvious since these were all infinite, but every one of these cosets has the same number of elements. In this case, they all have infinitely many elements, but it's possible, especially if you have a finite group. If you have a finite group, your cosets, since they partition a finite set, all the cosets will have to be finite. But we know they'll also all contain the same number of elements. So that's our next result. If H is a subgroup of a finite group, then the cosets of H and G all contain the same number of elements. And now we get kind of a big result. Lagrange's theorem says that if H is a subgroup of G, then the order of H divides the order of G. And here we're using the word order to mean the number of elements. And so if H is a subgroup of G, for example, here's one way we might use Lagrange's theorem, just really quick example, like a margin example. Let's say if G is a group, and I know G has like, I don't know, 12 elements or something, then it cannot, we know there will be no subgroup of order 5, for example. Right, I know in order to have a chance of being a subgroup, if anything is a subgroup of G, its order would have to divide the order of G. So possibilities for the order of a subgroup of a group that has order 12 would be like 1, 2, 3, 4, 6. I think that's it. But any subgroup G might have would have to divide 12 here. And now we're going to use this result to show another larger result. Let's say G is a group of order n, so it's a finite group. We're going to show that for any element G, that G to the n is equal to 1. We're not saying that n is the order of G, right? The order of an element is the smallest power we can raise it to get the identity. But what we're saying is if we raise it to the power of the order of the group G, then we know we'll still get the identity. So let's let P be the smallest positive integer such that G to the P power is equal to 1. We know that exists, by the way, right? We established some results on the order of an element previously. And we're going to generate a subgroup of G using this one, using the element little g. And if we're going to generate a subgroup, we're just going to generate that cyclic subgroup. So let's let H be that subgroup that we generate with the element G. So we know that H is a subgroup of G of order P. And now we can use Lagrange's theorem. By Lagrange's theorem, the order of H has to divide the order of G, so that means that P divides N. And if P divides N, That means that n is equal to p times k for some integer k. Now we're almost done. I mean, so we want to show that g to the n is equal to 1, is equal to the identity element. So let's find it. G to the n, well, n is equal to pk, so this is g to the pk. And we know we can rewrite this as g to the p to the k power. And what's g to the p power?
It's just 1 to the k power.
Yeah, so g to the p is 1, which makes this whole thing 1 to the k power. Yep. And so we just get 1. And that's what we wanted to show.